Okay, so for this part, we're going to talk about your applications of your electricity itself. So basically, when electricity flows through your light bulb or your lamp itself, it will light up, right? So basically, what this means is basically as current increases, your brightness will also increase. So you can see that they're actually a one-to-one. Basically, they are both affected. And because your current and your voltage, your PD, right, is also your potential difference here. PD is actually, if you remember, is V equals to I times R, right? So because it contains this I as well, as your voltage increases, the brightness will also increase. But most of the time, we are actually going to use your current. So normally when we describe your brightness or your anything else related to your application, most of the time we're actually linking it back directly to current itself, because even your own voltage depends on current. So unless the question only gives you voltage, or you're more familiar with using voltage itself, then use the voltage explanation itself. So you can see as current increases, brightness increase. So what affects current? Don't forget I is V over R. So basically, it is because of these two relationship itself, you can say that number one, my resistance decrease. Therefore, I have more current. Number two, as voltage increase. That's why you have this. So you can see this one, there's actually a extra part. As voltage increase, current also increase. Therefore, brightness of my light bulb increases. That's the relationship there. Okay, so do take note about this. So for example, if you see this diagram itself, this is one of the harder questions, but they do test this quite commonly itself. So you can see over here, I have two identical light bulbs, X and Y, and you then attach Z to parallel to X only. Okay, so in figure 3.2, which is the one on the right, compare the brightness between X and Y. So whenever we say compare the brightness, the first thing you want to ask yourself is, what is the current of X? What is the current of Y? So you can see over here, as current flows through, because of this small little dot, what happens is current will split into two parts. Because this part is parallel, right? And then what happens? You'll merge back again and you'll flow like this. So you can see that the current of Y is actually the current of X plus current of Z, because this is actually a parallel part for your chunk over here. So to illustrate with colors, this part, all the parts in green are your total current, whereas the yellow and the blue are for your individual branches. So you can see that the yellow and blue will add up to give you green over here. All right. So how do you compare the brightness? So first thing you want to straight away say is the bright. You can say that lamp Y is brighter than lamp X. Explain why. Basically, you can say that the current flowing through lamp X, or you can say current flowing through lamp Y, is the sum of the current flowing through lamp X and that of lamp Y. Lamp Z, sorry. Okay, so because it is this, since there is more current through lamp Y will thus be brighter. Okay, so this one just goes back to the link where you have more current, you have more brightness. This one is just in case it's a 2 mark or 3 mark itself, you want to double check which is which. Because if you notice, this compare part is actually 1 mark. Your explanation itself could be 1 or 2 marks. So you need to be a little bit more careful. You might want to just link it back to the question. What's the relationship between current and brightness? Just be a bit explicit. Just say more current, brighter. That's all. Just have one short line at the back to link it back to the question. Okay. So now, how does the brightness of the lamp change? So this is actually comparing from 3.1 and 3.2. So the first thing you want to actually ask yourself now is, what happened in 3.1? So in 3.1, you can see that this is actually a series circuit. So what does that mean? The current here, IX, is IY. They are exactly the same. This is your total I. Okay, this is your total current flowing through both of them. Okay, so since the current actually is the same, you can actually say that number one, first thing you ask yourself, from X, from 3.1 to 3.2, what happened? You can see that the current over here was originally your total current, right? So you can just imagine you had a lot of current flowing through X at the 3.1. But what happens is when you add Z, when lemZ is connected parallel to lemX, the current flowing through lemX decrease as the effective, it just decreases. Okay, because when you have a parallel circuit, your current now will become split into two parts. So because of when lemZ is connected in parallel to lemX, the current flowing through lemX decreases. Hence, the brightness of lemX decreases as well. Okay, so this is for lemX. You can see the X actually become dimmer. Okay, so next one. What about lemY itself? LemY, you can see that previously was total current, same as lemX, right? So they had the same amount of current flowing through at this point. But what happens is when lemZ is added. Now the thing is, if you look at Y is actually your total current, right? It's actually your new total current. Okay, so what's your new total current itself? Don't forget what is total current. Your total I is total V over total R. So now ask yourself, if I just add Z, what changed? This one is the same because we still use the same battery. This one actually decreased. Okay, so what we want to say is the effective resistance of the circuit decreases. Okay, so when it decreases, what happens is that the total current flowing through lemY increases, and thus the brightness of lemY increases. Can you all see that? So basically, you need to stare at it very, very carefully. You are only comparing the current of that particular device that you are measuring itself. So you are just looking at lemX. You only want to focus on the current in lemX. So previously it was a certain value, and because I add Z, what happens is it will split. And because Z is actually identical as well, you actually split nicely in two, just that your value itself may differ slightly, but you can still see that your current itself will actually become much smaller. So even though, yes, the total current, the green one, is actually bigger, so that's why Y is brighter, right? But don't forget, even though it becomes bigger, it also divides by 2. So because to give you your yellow and your blue color current, right? So the yellow current is actually just half of your new total current. So because of that, brightness, the current flowing through X will also decrease, brightness will also decrease as well. Okay, so you can see over here, basically you can see current decrease is the same thing. All right. So just be careful. So when you're parallel, you can see we are going to use selected parts of your explanation itself to kind of target why is this particularly so. You want to go straight directly to the relationship. What happened? Something must change to affect the current, and if my current is affected, therefore my brightness will also be affected. Okay, so you just need to be very careful. This is one of the trickier questions that could come out in exam. So apart from lighting up your light bulbs or whatsoever, we mainly use electricity in terms of what? In terms of heating effect. So basically, you just need to remember when current flows through any device will heat up. Okay, you will always heat up your device. That's why if you use your handphone for a period of time, or you play your video games, or you watch a video very, very high definition itself, you realize, how come the back of my phone started to heat up? Because when you want to watch all these very, very high definition or you play your video games itself, a lot of your current is flowing through your handphone, and they will actually produce a lot of heat as current flows through. So because of this, we actually want to make use of, number one, high resistance material when you want to produce heat, and we'll use low resistance material when you want to reduce energy loss. Okay, because this heat produced can be seen as your undesired energy loss. So because of this, you need to understand electricity is also a very, very, how to say, very, very real world application question. It's very, very applicable to your day-to-day life. So always be curious and ask yourself, how come this happens? How come this happens? How come my handphone heats up? How can I make it more cooler and stuff like that? All right. So number one, if you want to use high resistance, we have this material itself. This material is what we call nichrome. So if you ever go overseas next time, go to a hotel and you'll notice that usually they'll give you an electric kettle, right? Open it up and you'll notice that there's this spiral, silverish spiral inside. This is actually made of nichrome. So the good thing about nichrome is resistance, it can produce heat very fast. Okay, when the current flows through, you can produce heat very, very fast. Okay, and similarly to your low resistance itself, we use copper. Now, in the middle, you see your tungsten, right? This is actually for your light bulb. Okay, so the thing is, why you can actually produce light is actually this, basically this guy heats up to produce light. So actually your old light bulbs itself, they're actually very, very dangerous. So when the creator, if I'm not wrong, it's Thomas Edison, is when he was creating the light bulb itself, it exploded very, very often and he had to waste a lot of money and effort just to make it. But he persevered on and he managed to create the safe light bulb that we use. But because it's actually quite a dangerous device, now modernly, we all change to your LED now. So LED itself is actually a little bit special. It doesn't actually produce a lot of heat. It will actually use electricity to directly create light. So rather than using a light bulb that uses heat to produce light, LED is a little bit different. Okay, so that's why we're not going to focus too much about this, but you need to know that tungsten exists. It's a special metal that have a very, very high melting point. Okay, so do take note, high melting point. So apart from that, we talk about your copper. Now, copper is something that we use very, very often in our wires itself. The good thing is because you have very low resistance itself, is that this will actually minimize heat loss. So basically your energy loss. Because don't forget, heat is just thermal energy. Okay, so you can actually minimize your heat loss so that you can supply more electricity to your devices. So for those people who love music very, very well, sometimes if you buy your very expensive instruments or your home surround system or whatsoever, you know, if you were to go and double check on the very, very good ones, the very high quality ones, sometimes they use silver wires instead. That's why it's so expensive, because silver actually have lower resistance than copper itself, and therefore because you have a lower resistance, you can actually supply more electricity to your device and you can hear a better quality of sound. Okay, now apart from your light and your heat, we can also use electricity to make magnets. Okay, so one thing special is more of a good to know is that when current flows through, you can produce a magnetic field. So basically you can just imagine if current flows through here, you actually produce like behave like a magnet. So if you put this iron nail inside, the iron nail will actually become magnetized. So we can actually make it into a magnet by using electricity to wrap around it. Now do take note, these are all insulated, which means that there is no electricity in the iron nail. It is just around it, wrapping around it, but it's not flowing inside the iron nail. Okay, because some students be like, "Sure, isn't this dangerous? Your wires is touching my nail." The wires are insulated. They are wrapped around like rubber or something else. Okay, so you don't need to worry about getting shocked when you touch the iron nail. All right. So the thing is, you can see in the diagram itself that the wires are wrapped around it, right? So if I have more turns, by the way, if you don't know this, this is your coil of wire. this word solenoid is coil of wire. So basically, if I have more turns around the iron nail itself, I will have stronger magnet. Okay, if I have more current out, which makes sense, right? Because if you have more current flowing through your wire, you will therefore also have more magnetic force, or the magnet will become stronger itself. And you don't need to worry too much about this soft iron core part because we're already using an iron nail. So what this also means is, if I don't have the iron nail, I can still make a magnet. Using just my wires, I can still make a magnet. Just that this magnet will become very, very weak. So I need this iron nail itself to actually make it even stronger itself. Okay? So do take note about this. Next part is actually your chemical. So some of you might have learned this in your chemical reactions or your chemical changes, chemical bonding chapters already. So the thing is, we are going to use electrolysis to actually break down, in this case, water itself. So ask yourself, water is H2O, right? So what happens if you use electricity, you can actually break it down into H2 gas and O2 gas as well. So do take note, H2 and O2, they are diatomic. So we need to use H2 and O2 itself. So if you balance the equation itself, this part you need to add 2, this one you need to add 2. So you end up with this. So if you notice the ratio, right, you have 2 hydrogen and 1 oxygen, right? So you can see on this side, this is 2 times, this is 1 times. So you can see the amount of gas that you produce is in that ratio itself. So that's why you have your electrolysis. So this is also the reason why water can conduct electricity, because water can be broken down into H2 and O2. Okay, and O2 is very, very dangerous. That's why if your lightning strikes the water, usually you see an explosion, right? Why is that so? It's because the oxygen can also explode, can combust, and it can explode in air. Or because electricity, your lightning, right, if it strikes the ocean, it produces so much hydrogen and oxygen in that short amount of time that it just basically is like a very big bubble that just bursts straight away. So just boom, straight away. All right, so just do be careful about all of this. Next one, your electroplating and your purification of metal, right? They actually work very similarly in the same way. So first thing is, we know that conventional current flow, we always move from here to here, correct? So inside, using this liquid, which is going to be just a ionic liquid, right? So the thing is, you'll notice that your current should flow from the copper itself. This is just a copper rod, okay? And you will be to this iron key itself. So what happens is that will actually form a thin layer around your iron key itself. So this is actually an iron layer itself that is, or not layer, coating. So what happens is, we know that iron rusts very, very easily, right? So to prevent it from rusting, as you can see over here, to prevent it from rusting, right? What happens is, we'll coat the iron key with a layer of copper. So what happens is, by putting this setup itself, we are actually using electricity to actually allow some of the copper itself from your copper rod to actually be transferred to your iron key itself. So we don't actually need to melt the copper, because copper has very, very high temperature, right? So instead of using such a high temperature, because it needs a lot of money and you need to have the equipment, you can do a very, very simple setup where you use copper and you use a solution that has copper ions. You can actually transfer your copper to the iron key itself. Basically, you can just imagine your electricity flow through. I have some copper that leaks out. Because you have too much copper, you have to form it on this side. So you can see, because the current will always flow from the positive. So remember, this is positive, this is negative. So you move from positive to negative until it coats the entire iron ring, iron key itself. So once you feel like the layer is thick enough, then you can stop the process, and then you can safely remove your copper coated iron key. So you don't need to always coat it with copper. You can actually coat it with other metals as well. So that's why actually, if you go to those kind of pasar malam or those kind of bazaar night markets itself, you see that they sell some rings or some jewelry or accessories very, very cheap compared to those kind of jewelry shop, right? You go to a jewelry shop, it's like few hundred, few thousands. But if you go to those kind of like small little markets itself, where they sell the jewelry that looks perfectly the same, shiny and all that, it is actually because they are actually just thinly coated with the silver or the gold outside. So if you were to scratch those cheaper items, you'll notice that there is a different layer below. So it's actually just a very, very thin coating itself. So don't be scammed. But basically, if you are going to buy just a cheap gift for your friend, sure, feel free to do so. But if you're buying it, investing it for gold or silver or diamond as a very important gift, like birthday gift or whatsoever, please be careful, mindful of how much you spend and all that. Right? Then next one over here, purification of metal. So you can see over here is that we have this very impure copper. So it's probably an alloy of some sorts. Okay. Then you have this very pure metal. Okay, so you have this pure metal over here. So same thing, current will flow from positive to negative, right? So you can see that your electrons, your ions, your negative charges your charges will just flow from plus to minus itself. So when you have this very impure copper itself, what happens is that you want to just transfer the copper to the right hand side itself. So the right hand side is just pure copper. So as the copper transfer from left to right, this one actually gets smaller. Give me a second. Huh? Okay, so back to where we are. You will actually end up being smaller, and this one actually get bigger and bigger over time. Okay, so what happens is that you will become like this. Okay, so you will, from start off, you have a very big piece, and this part is just a very, very thin, small little rod. As time passes, you will notice that the rods will actually change in size according to what you have. And a lot of the impurities will actually just fall off at the bottom. So you can just collect it back, melt it down, and then you shape it into a rock all over again. Okay, so you'll notice that for both of them itself, the desired item that you want will always be at the negative part. Okay, and the ones that you don't want, or is the material that you want to use, will be the one on the left. So right is your results, left is what you're using. All right.